Hello everyone. So today we talk about chemical equilibrium. What is the composition of a reaction mixture of ideal gas? What are the partial pressure at equilibrium? Okay. So if you take a reaction like this, what is the partial pressure of nitrogen, hydrogen, and ammonia at equilibrium? So for defining this, we need a quantity like what is the mixture? Is this mixture in equilibrium? We can answer by finding delta G if you allow the reaction to proceed further. Um, to give time to take the reaction to proceed small amount. Okay, for from that you can calculate the delta G. Okay, that is change in Gibbs energy for the reaction. Okay, G is nothing but summation of Ni mu I for ideal gas in a mixture. Okay, so delta G is uh, for product minus reactant. Okay, where psi is an arbitrary small number that allows to let the reaction proceed just a bit. Okay, to further. Okay, we know this formula mu I equal to mu I naught plus RT ln Pi. Okay, so this is come from the delta G, the fundamental equation formula delta dg equal to vd, like that. So at constant temperature minus STT, so the dt becomes 0. So deriving for substitute minus vdp. Okay, by substituting v for RT by P, you got this relation. The delta G is nothing but the mu I. Okay, where mu I T is the standard chemical potential of species I at 1 bar and in a pure state. Okay, we take at a pure state. Okay, so normally this is initial and this is final. So changing gives free energy. Okay, so we take the initial state as a standard state. Okay, then delta G is delta G plus RT ln Pc, and here the partial pressure of the gases. Okay, we take this is as ln Q. Okay, and this is the standard gives free energy, and this is the reaction coefficient. Okay, delta G is the standard change in free energy for taking pure products into pure products, pure reactant into pure products. Okay, delta G is standard. The zero means standard. Okay, product to reactant. The delta G is when less than 0 means reaction proceed to more product. Then delta G greater than 0 means the backward reaction is spontaneous. Is equal to 0 means no spontaneous change. That is become equilibrium. Okay. So at equilibrium, delta G is equal to 0. Then delta G not equal to minus RT ln Q. Okay. So this is the formula. So you take this formula. So when delta G becomes 0 means delta G not equal to minus RT ln Q. Okay. Define quadrant at equilibrium is Kp. Okay, the equilibrium constant. For at equilibrium, the reaction coordinate is called equilibrium constant. So just changing the symbol Q equilibrium to Kp. Okay, so pressure is nothing but you can write the pressure as a function of partial pressure and mole fraction. Okay, so take the partial pressure outside and the mole fraction here. Then this is the Kx. Delta G reaction is equal to minus RT ln Kp, Kp equal to, so then the another form is Kp equal to e power minus delta G RT. So take the minus here, so minus delta G divided by RT equal to ln Kp. Okay, so taking both side e power means, so ln cancel out, so ln is nothing but the base e. Okay, so taking e power means the ln cancel out, and you got Kp equal to e power minus delta G by RT. Okay, is not a function of total pressure. Okay, kpt is not a function of total pressure. It is p of minus delta v. So it is delta v is nothing but the partial pressure of cd minus ab. Okay, c plus b minus ad. Okay, recall that all partial values are divided by 1 bar. So kp and kx are both unitless. Okay, so like if you take a reaction hydrogen plus carbon monoxide, it gives H2 and carbon monoxide. So the initial moles is A, B and 0. Okay, so this is products. Okay, initially it's 0. Oh, number of moles at equilibrium. So A moles of H2 reacted, B moles of CO2 reacted, X moles of H2 formed and X moles of CO formed. Okay, so the total mole is just adding all these, you get the total number of moles at equilibrium. Mole fraction is number of moles. So mole fraction is nothing but moles divided by total moles. Okay, mole fraction, if you take mole fraction of XA means Na divided by N. Okay, N is the total mole, it is the moles of A. Okay, so delta G formation, standard delta G. So you can, it is from, you can get the table of these delta G for different compounds. Okay, for carbon 0 for H2O. Okay, for 0 for H2 gas. Okay, and this is for CO2 and this is for H2O and this is for CO. Okay, so delta G for reaction is adding these, all these, you get the answer. Okay, with the stoichiometric numbers here all one. Okay, so product minus reactant, you got this 28.6 kilojoule per mole. Okay, so Kp is e power delta G divided by RT. R is gas constant and temperature 298 Kelvin. Okay, so Kp is nothing but here. So another form Kx of mole fraction of H2, mole fraction of CO divided by mole fraction of H2 and mole fraction. If you take mole fraction as x into x square divided by a minus x into b minus x. Let's take A is equal to 1 mole and B is equal to 2 mole. We need to solve this equation. Okay, how much amounts of, so using approximation method, k is equal to less than 1. So we expect x is also less than 1. Okay, here you see this is the k value 9.7 into 10 power. So here what is the k value obtained? 9.7 into 10 power minus 6. Okay, so it is very less than 1. Okay, 0.00050 after 9 is 1. Okay, so it is very less than 1. That is you tell. Okay, when k is less than 1, we can expect mole fraction is less than 1. Okay, so when mole fraction less than 1 means 1 minus x approximately equal to 1 and 2 minus x approximately equal to 2. Okay, to find x is nothing but the amount of moles at equilibrium. Okay, so we find this is the x. Okay, number of moles at equilibrium, that is x. Okay, how much it reacted, so x square divided by 2. Okay, so solving this you get the value of x is equal to 0.0044 mole. Okay, you can solve this equation exactly. Okay, so using this formula. Okay, if you solve this formula you get the answer, same answer, approximately same. Okay, the negative sign gives a non-physical result. Okay, negative x values, take the positive sign only. Okay, if you solve this equation here, plus or minus 1, you get both positive and negative value. Okay, so negative is you cannot get a negative x value because x is the number of moles of product. Okay, so you cannot, it cannot be negative. Okay, so only take the positive value, you get the same value. Okay, Effect of total pressure. Okay, if you take N2O2 gas to decompose into 2NO2 gas, initial moles N 0 and number of equilibrium moles at equilibrium equal to N minus X 2X. Okay, and mole fraction is if you add these all, you get the total number of moles and divided by the N minus X divided by total moles and 2X divided by total moles. Okay, okay, mole fraction at equilibrium. So same partial equilibrium constant is partial pressure of NO2 divided by partial pressure of N2O4 is nothing but pressure. Okay, pressure is nothing but partial pressure into mole fraction. Okay, you get cancel out P into P, you get this, and if you solve it, you get this answer. Okay, and take alpha equal to x minus n, and just mathematics. Okay, if you increasing pressure, alpha decreases. If you here you take here increasing the pressure, here power is minus 1 by 2. Okay, so increasing pressure decrease the value. Okay, so decreases the alpha value. So alpha is nothing but x by n. Okay, alpha decreases means x is also decreases. Okay, so increasing pressure alpha decreases, x decreases means the reaction goes this way. So increasing pressure, here 2 moles of gas, here 1 mole of gas. So increasing pressure uh, take the reaction to reduce the number of moles of gas. Okay, so if you reduce the number of moles of gas, the pressure, increasing pressure you can withstand it. So that is the Leach-Atlas principle. Okay, so increasing pressure shift to the equilibrium so as to decrease the total number of moles or reducing the volume. Okay, so simply Leach-Atlas principle says that if some reactions go into more number of moles of gas, if you increasing the pressure, the equilibrium shift to reduce the pressure. Okay, by decreasing the number of moles. Always equilibrium tend to be equilibrium. You cannot, if you try to push the reaction high temperature like that, the equilibrium tend to maintain the equilibrium. Okay, so increasing pressure shift the equilibrium towards the reactant. Okay, in the previous example. Another example, NO plus O2 plus 2 NO2 gas. Here the initial moles is 2, 1, 0. Okay, and number of equilibrium moles and mole fraction same, and the Kp. So here Kp is greater than 1. Okay, so this is the equilibrium constant 2.3 into 10 power 12. Okay, here Kp is greater than 1. Okay, meaning x equal to 1. Okay, then you can solve the equation. X equal to 1 means if you put x equal to 1 means here you put x equal to 1. So 3 minus 1 equal to 2. X equal to 1 into 1 square. 1 minus 1 equal to 0. Here reduced the equation to 1 minus x cube equal to 2 by p kp. Okay, x equal to, so simple mathematics. If you tried, you can understand this. So here increasing the pressure, then x expected from the Churchill principle. Here increasing the pressure, here positive value. So here positive power. So increasing pressure means the below value increases. The below value increases means the total value decreases. So means the x is increases. Okay, so here like here, if you increasing the pressure, x increases means the reaction goes forward, because here 2 moles gas and 1 mole, 3 moles of reactant, only 2 moles of product. So increasing the pressure reduce the number of moles. Okay, so just as to maintain the equilibrium, they tend to become towards to reduce the how much you, if you disturbance, if you try to disturb the equilibrium, The equilibrium tends to adjust with the equilibrium or adjust with the disturbance. Okay, so if you increase the pressure, it goes forward. If you decrease the pressure, the reaction goes backwards. Okay, so it is useful when the if you want to go the reaction forward or backward. Some reaction does not go forward in the room temperature at room or atmospheric pressure. You must do some reaction goes in exothermic, some reaction at endothermic. You should increase the pressure to make the reaction forward, or you should some examples you should decrease the pressure. Some example you to increase the temperature, or some example you should decrease the temperature. Using these calculation only you can calculate you should decrease or increase the pressure of reaction. Okay, we can take see the examples. Equilibriums and solutions. Okay, the chemical potential for molecules in solution is given by the formula that is very similar to that for ideal gas. So solution also the equation same, chemical potential formula is same, but the here the not partial pressure, these are concentration. And the standard chemical potential is for ideal gas it is for 1 bar like that. Okay, for an solution we defined given pH, salt concentration, etc. For standard chemical quotient we standardize some condition. Okay, for calculating standard chemical potential. Okay, then the other reactions are same. If you take an example, solution A, B, and gives C and D, so the gives free energy same. The at equilibrium they become equilibrium constant K is same, concentration or equilibrium concentration, the formula same, temperature difference of K. Okay, so if you want to determine the temperature difference of equilibrium constant, just differentiate with respect to temperature. Here also differentiate with respect to temperature. You got delta G divided by RT square minus 1 by RT d delta G by RT. Okay. Okay. So here they used the UV formula. Okay. Okay. So if you differentiate this, you get this. But at a fixed pressure and our solution properties, pressure equal to 1 bar, pH constant, etc. We defined this as at a fixed 1 bar, pH constant, etc. Okay. So then, so if you take, so this is from fundamental equation. If you differentiate with respect to temperature at constant pressure, you got minus entropy. Same. Okay, for Gibbs free energy, for change in Gibbs free energy, and this is become delta S. Okay, normal Gibbs free energy means S, change in Gibbs free energy means delta S. D ln K divided by dt equal to same. Okay, so here just putting this. So if you see the equation, this is delta G for delta G standard. Okay, so then here they replaced with the delta G nothing but delta H minus T delta S. Okay, at the standard. Okay, so and then replace this d delta G by dt is nothing but delta S, so become positive RT. Okay, so then these two are cancel out. Okay, because this is negative, this is positive, these two are cancel out, and you get the answer. Dependence of ln K with respect to temperature. Okay, this is nothing but enthalpy divided by RT square. So then integrating with so integrating this equation from temperature 1 to temperature 2, you get ln 2 T2 minus ln T1, and take this in right hand side and differentiating with respect to delta G. Okay, so when the so at constant pressure delta H is equal to nothing but delta Cp T2 minus T1 or T minus T1. Okay, so same. So then substitute for delta HT here this equation. For a small range, these can be assumed to be small and delta H be independent of temperature. Okay, so then you can take outside delta H by RT, you can take outside, and so over a small temperature range. Okay, over a small temperature, and delta Cp is assumed to be small. Okay, so delta Cp is nothing but the change in heat capacity at the temperature range. It is mostly constant. Okay, so mostly constant. So for the given temperature range, it is very small. So you can neglect this term. Okay, only delta H by RT here. So different. If you take the delta H divided by R outside, because these are constant, because delta H is independent of temperature, then 1 by t square nothing but 1 by t minus 1, and if you substitute the limits, you get the 1 by t1 minus 1 by t2. Okay, these are mathematics, you should know. Okay, so when the delta H less than 0 means exothermic, the equilibrium shift towards reactant. When the greater than 0 endothermic, equilibrium shift towards products. Okay, so if you see here, when exothermic means T2 is greater than T1. Okay, the final temperature, then Kp of, so I already told. Okay, when some reactions are exothermic means you should if you, when increasing the temperature, the equilibrium shift towards reactant. Okay, if reaction is endothermic means the equilibrium shift towards product, because uh, if the reaction is exothermic means the reaction gives heat, excess heat. um, if you also giving heat means the reaction tends to become product side. Okay, so then only you should avoid the heat. Okay, like that. If your reaction is endothermic means you, if you give heat means the reaction takes the heat and proceed to products. Okay, shift the equilibrium shift towards the product. Okay, like that. Like pressure also, like pressure, if you reaction, if you increase the pressure means it reduce the pressure, like that. If you, the exothermic reaction means if you increase the temperature, it try to reduce the temperature. Okay, that is the concept. So the Haber process, it is a very important process, because tons of tons ammonias are prepared for uh, fertilizers, like that. Okay, it's the most important chemical process. Here the delta H is and the delta G is given, and Kp is nothing but partial pressure of ammonium divided by partial pressure of H2 and partial pressure of N2, and see pressure of H2, and here if you take substitute with the partial pressure and mole fraction, you get this relation. And Kp you got 860. Okay, by substituting delta H and RT. Okay, for 1 bar pressure, this is pretty good, lots of product. However, the reaction at room temperature is slow. This is kinetics. Okay, so for 1 bar, the product, lots of product get to, but the reaction is very slow. Okay, um, so when you raise the temperature from temperature to 80 Kelvin, can speed up it reaction, can speed the reaction. But since delta H is less than 0, here you see the delta H is minus 46.21 kilojoule. Negative means exothermic. Okay, so lead saturated pencil, if you increase the temperature, the equilibrium shift towards the reactant, because the delta H is negative. Okay, so increase the temperature, shift the reaction towards the product. Then if you calculate the Kp 0.00 become. Then what to do? Then note Kx is nothing but P into Kp. So if you increase the pressure, you can increase the Kp. Okay, that is the formula. Okay, like again use this and but with the pressure, if you increase the pressure, the equilibrium shift towards product. Okay, here you see here half gas. Okay, here 3 of gas, here 1 gas. Okay, half plus 3 of is nothing but 4 by 2. 4 by 2 is nothing but 2. Okay, 2. Okay, here 2 moles of gas, but the product 1 moles of gas. Okay, so increasing the pressure reduce the number of moles of gas. Okay, so shift towards product. Okay, here 2 moles of gas, reactant is 2 moles, product is 1 mole. So increasing the pressure reduce the number of moles. Okay, because 2 moles of gas increasing the pressure, lots of gas, it should reduce the number of gas. Okay, so that reduce the pressure, it can withstand the pressure applied. Okay, so that is the concept. So at a high temperature and high pressure, you got the Kp 0.007. So So at 1 bar and T Kelvin, at P equal to 100 bar, just multiply this with 100, you get 0.7, much better, okay. So you see the application of the Gibbs free energy like that, okay. Heterogeneous equilibrium. If your product or a reactant is a solid or liquid, it will not appear in the ratio of partial pressure for Kp or in the concentration if the equilibrium is in solution. However, it needs to be used in delta G. So here we what they say is here you take this is solid A and this liquid C, okay. So if you calculate the delta G, the solids and chemical potential of solid and liquids are present in the delta G, but they cannot appear in the partial pressure because solids and liquids does not have the partial pressure, okay. So you should remember this, okay. So it cannot present in the partial pressure, but it should but still have the in delta G, okay. So example, decomposition of limestone. Here the limestone is solid and the calcium oxide is solid, carbon dioxide is a gas, okay. If you calculate the delta G, this is the delta G. The equilibrium constant includes only the gas, okay, but the delta G includes the solids too, okay. So you should never remember this. Equilibrium pressure ln Kp is equal to delta G divided by RT. Nothing there at room temperature. Try one. So at a room temperature, the Kp is very very small, 10 power minus 23. Okay, so it cannot give the product. So at increasing the temperature gives a much better result. Okay, because you see here delta H is, if you find the delta H, the delta H must be negative. Okay, so that positive. Okay, so that increasing the temperature help the reaction to proceed. Okay, there is probably some change in delta H over such a wide range of delta G must be changing, but clear the equilibrium shifted dramatically. Okay, so here we take the delta H because it is independent of temperature, that you can take outside the integral. But here the temperature range is very large. Okay, room temperature to 1100. Okay, so it is a very large temperature. Definitely the delta H is changed, but clearly the equilibrium which so but that's not matter. We only we want the equilibrium shifted towards product or not. Okay, so clearly the equilibrium shifted towards product. Okay, because delta H is negative. Okay, so then increasing the temperature decrease towards products. Okay, so you should so you cannot say simply by the delta H negative or positive. You should derive the formula and you should substitute in the formula. Then only you can determine it is proceed to the product or not. Equilibrium. So application to drug design. How they these calculations are application applied to the drug discovery like that. Okay. So if you take analysis for equilibrium that we have used for reactions involving breaking and making of covalent bond applies equally well to reactions such as ligand acceptor binding, where the ligand and the receptors are proteins. Okay, in biochemical reaction like that. Okay, so if you take R is a receptor plus L is a ligand equal to complex. Okay, complex is ligand plus receptor. Okay. Okay, if you take this reaction, R is a receptor, L is a ligand, C is a receptor ligand complex. The interaction between these proteins typically involve multiple non-covalent interactions, including hydrogen bonding, hydrophobic interaction, electrostatic interaction. Definitely, there are a lot of interaction. Okay, so the equilibrium constant gives free energy change for the reaction are related to the usual way, delta G equal to minus RT ln K. Okay, where the equilibrium K is called the association constant. Uh, so like that, product divided by reactant equilibrium constant is nothing but product divided by the standard state needed to characterize delta G is defined at a set of specific conditions. So always needed to specific specific reference condition, pKa salt condition for the standard delta G or standard any standard condition. Okay, for the reverse process. Okay, the reverse process is a dissociation. Okay, dissociation of the ligand from the receptor. Okay, used to characterize the strength of ligand binding through the equilibrium constant Kd. Okay, Kd is the for reverse process, Kd is dissociation constant. For the forward process, Ka is association constant. Okay, just like receptor plus ligand gives the complex. The complex after the ligand come out of the receptor, then the reverse process taking place, dissociation. Okay, so dissociation is just the reverse, receptor plus ligand divided by the complex. Okay, the lower the Kd, the better the ligand. Okay, so when the dissociation constant small means it cannot dissociate fast. Okay, so the better the tighter the bonding. Okay, tighter the binding. Okay, in an experiment, the ligand is typically labeled with radioactivity iodine 125 and added to cell under conditions that prevent the ligand from being internalized 4 degrees Celsius. The ligand is usually in great excess compared to the number of receptors, so that at equilibrium, so if you take ligand is greater, okay, compared to the number of receptor, okay. So if you take ligand so much excess means then ligand is L0 is a good approximation, okay. Meaning that it is same as initial ligand concentration. It does not change very much, okay, because it is high. Taking one or two ligands does not change the initial concentration, okay. So it is a good approximation, okay. It does not the same, but it is a good approximation. It can effectively change during the process, okay. If RT is the total concentration of the receptor, then RT is R plus receptor, okay. If total RT is total number of receptor, okay, then the receptor, some receptor is freely, some receptor is combined with the ligand to give the complex, okay. So that is the total. Then substitute R total equal to RT minus C equilibrium divided by C equilibrium into L0, okay. Then rearrange the equation, you get the relation, okay. The value of Kd and thus delta G can be obtained by measuring the concentration of complex formed at various initial ligand concentration L0 by plotting C equilibrium L0. So just y is equal to mx plus C formula, okay. By plotting y into x, so y is nothing but C equilibrium divided by L0. X is nothing but C equilibrium, okay. X is C equilibrium. So m is nothing but minus 1 by Kd, okay. So the slope gives 1 by Kd. Minus 1 by Kd means negative slope, okay. Okay, the fraction of receptor occupied is, so just to rearrange the equation, you get this relation. So when the ligand concentration very less than the Kd, then the C equilibrium divided by RT equal to L0 divided by Kt, okay. When this is high means you get this relation. So these are mathematics you should know. Although free energy for receptor ligand binding reactions are generally determined experimentally through Kd, it is possible to so normally the free energy are determined experimentally. So it is, but it is possible computationally estimate the change in free energy that accompanies the point mutation in one of the amino acids in the ligands. Okay, this approach can be used to design a new and better drug that binds with an affinity that improves its property. Okay. So if you then example of such designed multi-ligand improved version of granular site colony stimulating factor. Okay, so it is just designed ligand. Okay, so by designing the ligand, you can determine how much the affinity. Okay, so grow. So it is a protein drug that used to treat chemotherapy patient and stimulate the growth of white blood cell. Okay, so it is a protein drug. Okay, so taking this drug stimulate the growth of white blood cell. Okay, so it is important to bind the drug with the receptors of the body. Okay, and you should it also should go to the reverse direction. So because before it decompose by the enzymes into, okay, so we read this that is able to give bind tightly to the receptor at the cell surface. Okay, at a pH, at the cell surface pH is 7.5. As this ligand cell produce the desired proteins. Okay, but when the complex C is internalized in the cell in the endosomal components at pH 5.5, it is able for the to fall of its receptor to be recycled back to the solution to be used again. Okay, instead of being degraded with the endosome. Okay, if you take a cell like this is the drug, so it bind with the receptor. If when this drug go into the cell means here endozymes are there, that is decompose the drug. Okay, so it should be bind reback, so it should come, um, it should be desirable to fall off from its receptor. Otherwise it is degraded with the endozymes. Okay, so the designed principle for improved is weaker binding in at pH 5 point and stronger binding at pH 7.4, because in the outside cell pH is 7.4, the inside cell is pH. Yeah, so here the binding should be strong and here the binding should be weak. Then only it can recycle to back. Otherwise, it is decomposed. Okay, very much. So KD should be higher than KD is the dissociation. It should be higher in the pH 5.5 and lesser in the pH 7.5. Okay. So for a wild type ligand, the KD is at 7.4 is higher, and here 5.5 1.7 it is 0.5. Since delta G equal to minus RTKD, we get the difference of delta G for the dissociation reaction at the different pH. Okay, using this relation, if you know the KD, you can know the delta G. Okay. Okay, so this is two mutated form of the or improved version of the drugs. Okay, here these mutant synthesis and evaluated for the binding receptor with the following result. Okay, here you get the better result. Okay. Okay, so the mutant do bind more weakly than the does wild type. Okay, so the mutant bind more weakly than the at low pH. Okay, so that is the desired property. Okay, thus have the potential to be better drugs. Okay, if it is a weaker binding means it is better escaped from the endozyme. It is better escaped mean longer lifetime. Okay. Okay, so these are calculation. So what is the purpose is it is application. Okay, so how the application of these calculation used for the drug discovery like that. Okay, so it is a very important application. Thermodynamics is everywhere. Okay, for calculating these calculation, the thermodynamics is the basics. Okay, so okay, we come to the topic of phase equilibria in a one component system. Understand the general phenomenology of phase transition and phase coexistence condition for a single component system. The chemical potential controls the phase transition and phase equilibrium. Equilibrium condition at equilibrium must be identical throughout the system. You know that equilibrium condition psi must be identical throughout the system. When the multiple phases are present in equilibrium, psi must be the same in all phases. Okay, you know this. Then only the all phases are present in equilibrium. Otherwise, the chemical potential is something low is it will go into the that phase. Okay. We see the calculation. When multiple phases are present in equilibrium, psi must be the same in all phase. Okay, multiple phase in equilibrium must be same in all phase. Then only the all can coexist at equilibrium. Okay, for example, consider two phases, liquid and solid of water. Okay, if solid chemical potential and liquid potential equal means then liquid and ice can coexist. Okay, if the chemical potential of liquid is smaller than the chemical potential of solid, then the water is in the liquid phase. Okay, so like I already told the chemical potential like hill. Okay, so always tends to be low. Okay, okay, so when the solid is less than means the water is in the solid phase. Okay, then how does the chemical potential depends on temperature? So always tried. Okay, so always if you want some equation, always take from the fundamental equation, and mu is nothing but gives free energy divided by number of moles. Okay, so if you divide all these by moles, you get the delta, and if you divide this by moles, mean you get uh, molar entropy and molar volume. Okay, so S bar is nothing but molar volume. See, molar entropy is nothing but S by N. Okay, so G by N is chemical potential. Okay, So we want how depends on temperature. Differentiating with respect to temperature at constant pressure, you get to minus L delta S. Differentiating with respect to pressure at constant temperature, you get A power. So we know the calculations. The third law tells that entropy always greater than zero. Okay. So then the molar entropy greater than means this should be less than zero. Okay. So then only you got the negative sign, because the entropy is positive means this should be negative. Okay. So this should be negative. So you got the negative slope. This is d mu, this is dt. So dou mu divided by dou t at constant pressure. That is the slope. Okay. So I already told the differentiating delta, how the change the chemical. This is nothing but how the chemical potential change when the temperature change. How the chemical potential change here decreases, because here less than zero when the temperature change. This is nothing but the slope. Okay. Okay, so we all already know the entropy of gas is higher than the liquid, the higher than the solid. Okay, solid has the more entropy, more disorder than the liquid. Um, so entropy of gas is higher than the liquid. Liquid is higher than the solid. Okay. Okay. So for different chemical potential for gas, liquid, and solid. Okay, same. Just replace with the solid. Okay. So this is very important. Okay. So when the entropy of gas is very high means this is very steep. Okay, so the slope is very steep means here you see the slope is very steep. Okay, so negative slope is steepest in gas phase, and the liquid the entropy is small. Okay, so the steep is very small. Okay, and the solid it is high like that. So it is very important. Okay, so if you see the until the here it is solid curve, this is for liquid and this is for gas. Until the temperature of melting, the solid phase is lower chemical potential. So until the here you can also in the liquid phase, but the liquid phase is higher chemical potential. Okay, and until the boiling temperature, TB is boiling temperature, the liquid phase is lower chemical potential, and after that the gas chemical potential is lower. Okay, you see here this is lower, here this is lower, and here gas is lower. Okay, so this is the concept of entropy. Okay, so until the melting temperature, entropy of the solid is small, and until the boiling temperature, entropy of liquid is small, until the after that gas entropy is smaller. Okay, as the intersection between these two go, if you take these points, okay, at the melting point, the chemical potential of solid and liquids are same. Okay, because these two slopes are meeting each other. So at the intersection, the solid and liquid same. At the intersection, liquid and gas are also same. Here you see at the boiling temperature, liquid and gas are same. Okay, at the temperatures TB and TB, the two phases coexist in equilibrium. At other temperature, only the phase with the lowest chemical potential is stable. Okay, phase diagram describes the function of state variables, for example, in terms of temperature and pressure. So here the phase diagram. Okay, phase diagram is nothing but the change of state variables. Okay, so here this is the boiling, gas to liquid is boiling, here melting solid to liquid, and sublimation solid to gas. Okay, so this is the triple point and this is the line, this is the critical point. After this temperature, gas, you cannot differentiate gas and liquid, these two become same. Okay, or the melting line. Okay, so melting line, solid and liquids are coexist. Here you see the here the melting line, here solid and liquids are coexist. Here only solid has a low chemical potential and thus only stable. In this phase liquid only. So this is nothing but at this temperature and pressure. Okay, so at this temperature and pressure solid only stable, at this temperature and pressure this is liquid only stable here. And in the line, okay, so melting line. Okay, here solid and liquid are coexist. Okay, one equation, two variable, meaning two. This means that coexistence of two phases described by temperature pressure, or temperature as a function of pressure, or pressure as a function of temperature. Okay, line in the TB. At the triple point, okay, at the triple point, the chemical potential all three pieces are same: solid, liquid, and gases. Okay, You see at the triple point here, at the triple point, solid, liquid and gas chemical potential all are same. Okay, then only the triple point the three phases are coexist each other. Okay, the reason is the three chemical potential is same. Okay, two equation, two variables, this defines a unique point, so there is only one point. Okay, one point in the phase diagram. For water, 273.16 Kelvin and pressure is 0.0006 bar. Okay, at the critical point the gas liquid line stops. Beyond the critical point the gas liquid line, the liquid and gas become indistinguishable, they merge into a single phase. Okay, before after the critical point the gas and become single phase and it become indistinguishable. Okay, okay, in the single phase and the planar region. Okay, of the diagram, one of the chemical potential lower than the other two. Okay, the pressure and temperature can be changed independently without changing the pressure. Okay, at some the phase rule is 3 minus p for a one component system. Okay, f is the number of independent variable, also called number of degrees of freedom. P is the number of phases. Okay, so when the three phases are there in triple point, three phases are coexist each other. So putting 3 minus 3 equal to 1 mean 0. Okay, so degrees of freedom is 0 means there is no degrees of freedom. Okay, you should only one thing. Okay, can we understand the shape? Okay, the shape of coexistent line, that is we can get an equation dp by dt at coexistence. Okay, so how to understand the shape? Okay, line, that is slope of the coexistence lines. Okay, so that is nothing but that pressure variation with respect to temperature variation. Okay, to be predict using the state function, phase transition, phase equilibrium. Okay, if you take alpha and beta two phases at the coexistent line, the chemical potential are same for alpha phase and beta phase. Okay, at the temperature and pressure T. Okay, now take temperature to slight increase the temperature Tt, T plus Tt and pressure to Tp. Okay, staying on the coexistent lines. Okay, then chemical potential changes to little bit d mu and beta also d mu. Okay, and delta mu alpha equal to delta mu beta. Okay, because it is in the coexistent lines. Okay, the chemical potential does not change. Okay, the change is also same. Okay, but since delta g is minus sdt plus dv db, having change is same means the so these become equal. Okay, the delta g is nothing but delta g bar is nothing but delta mu. Okay, so g by n is nothing but the chemical potential. Okay, just dividing the Gibbs free energy divided by number of moles, that is the chemical potential. Okay, okay, so then this is should be same. Okay, on the coexistent lines means that means dp by dt at coexistent line is equal to, if you take this into this side and if you take this into this side, just rearrange the equation, you get this. Okay, this is nothing but the delta s, this is nothing but the delta v. Okay, at alpha to b. Another way to write this is using u equal to g bar equal to h minus d delta s. Okay, so another form of g is nothing but h minus delta ts. Okay, h is minus h for alpha and h beta. So delta h, so h alpha minus delta h beta equal to delta h, and if you take the delta s equal to this side, you can d delta s. Okay, using this term we can obtain the two terms, two forms of the Clapeyron equation. So this is very important. So dp by dt at coefficient is equal to nothing but ds by dv. Okay, or dh by d delta v. Okay, these two equations are very important. Okay, okay, now let's use the Clapeyron equation to understand the phase diagram. So let liquid to gas. Okay, take the phase liquid to gas. Okay, when the entropy is greater than zero and volume is very greater than zero. Okay, because um, disorderliness increases. Okay, become liquid to gas, the disorderliness increases, the volume also increases very much. Okay, so
So the delta S also increases, delta V also increases. The definitely it is greater than zero but small, okay, steep not steep, okay. So the line should be slightly greater than zero mean positive slope but not steep. If you get a steep means if you get positive value higher means you get a steep like this, okay, line, okay. So here it is very small, okay, because this is also greater, this is also greater, okay, something like 10 like 8 you get the small value, okay, 0 point like that, okay. So if you like they because this is also greater, this is also greater, and simultaneously this is very much greater, okay, then you get a positive value but very small, okay. So this line should be like that, okay. So when solid to gas, you take solid to gas, solid to gas, the entropy changes very much, okay, because solid the entropy is very very small, they are arranged very orderly. The volume change also very very large, okay. So if you take like that, here it is very very positive very high, and this is also very high, okay. So then you get a steeper line, okay. So here you got a very positive line, so you got a very steep line, steeper than the liquid and gas, okay. So this line like this, so it is useful for a other like that solid liquid gas also. For most of the substance, liquid and solids molar volume are equal, okay, approximately the liquids and molar volume of solid is very much equal, okay. So if you take a cup of water, okay, in liquid phase, and if you freeze it, you take a solid ice, if you measure the volume molar volume, these are approximately same, okay. So slightly decreased but approximately same, okay. But the entropy changing very much in the liquid phase, the entropy is very much than the solid phase, okay. So entropy is solid and the entropy is very, okay. So if you take the volume is same, but the delta S is greater, okay. So here if you determine the change, the delta volume is more positive, okay, solid to liquid. But the change in volume is not here, okay. You get a very steep because the above value is very much positive, the below value is very very small, okay. So you get a very steep line, okay. So the solid liquid line is very steep, so you should know these lines, okay. Raising the pressure above the liquid near or the squeezed line causes to freeze, okay, except for one of the most important substance on earth, H2. In this case, okay, if you take the example of for most of the substance, this is like that, the this like is this is very important. But if you take the water, okay, so in the water the solid phase molar volume is greater than the liquid, okay. So that the dp by dt is less than 0, okay. So if you take the delta v become negative, okay, so less than 0. So when the less than 0 means what happens, interestingly enough, silicon shows the similar behavior at much higher temperature, okay. Only the water and the silicon and silicon only at higher temperature, but water at room temperature. Here you see the water, the coexistence line should be like that. So water you get a negative slope, okay. Negative slope means you get this like that, okay. Solid liquid coexistence like this is negative slope, okay. So most of the gas it is positive, but when the water it is negative, okay. That is the difference between water and the reason for is molar volume of solid is higher than the molar volume of liquid, okay. So this is the existence, this is the reason why the earth only have the yeah, uh, living things, okay. If you take the molar volume of solid is higher, okay. If you take density, density is nothing but mass by volume, okay. So molar volume of solid is higher than means the density is lower, okay. More volume is higher than means the density higher. Then if you take ice, okay, here the water is the ice is be above, okay. In the at a lower temperature the ice is above, so that the living things can grow inside the water, okay. If what happens if the molar volume is less than means the density of ice is higher means the ice sink into the water and kill the animals, okay. So there is no possibility of animals living inside a water. Only when the density of ice is less than means the animals can grow inside the water, then only the all living things are created. So this is very very important property. This is why we living here. The another property of water is hydrogen bonding. That is also very important. Like if you take H2S, okay, there is no hydrogen bonding. Okay, in only in H2O there is hydrogen bonding. Only in the then only it can exist in a form of water. Okay, so the hydrogen bonding and this is the density, these are very very important. Okay, so these are the reason why the living things are here. Okay. Okay. Critical point and supercritical fluids. Does liquid to gas coexist or extend infinitely high temperature and pressure? No, it stop at a critical point. Okay, liquid and gas coexist curve stops at a critical point, you know. So above critical temperature and critical pressure, liquid and gas become indistinguishable single fluid phase. Supercritical fluids are finding remarkably practical application. Okay, the water, supercritical water is at 375 degrees Celsius, pressure at 221 bar. Organic molecule readily soluble, inorganic salt nearly insoluble. Okay, organic can be oxidized to carbon dioxide, N2, mineral salts, supercritical carbon dioxide. Reaction solvent replaces chlorinator and volatile organic compound. Dry cleaning solvent replaces perchloroethylene. Okay, so using the critical solvent, you can use uh, organic molecules readily soluble. Okay, inorganic salt nearly insoluble. Organic compounds can be oxidized to carbon dioxide, N2, and mineral salt and supercritical carbon dioxide. Okay, so these are the applications of critical points, critical fluids. Okay. Okay, so Clausius Clapeyron equation. Okay, first we saw the Clapeyron equation. Here we saw the Clausius Clapeyron equation. Let revisit solid gas and liquid gas equilibrium. We can make an approximation. Okay, so the volume of gas is higher than the solid and liquid. The delta V sublimation, delta V vaporization, delta V gas. Okay, V gas. We can ignore the molar volume of the condensed phase compared to the gas. Okay, condensed phase is liquid and solids are condensed phase. Okay, so taking the Clapeyron equation. Okay, for solid gas equation and using the approximation above, you got dp by dt equal to delta H sublimation divided by delta V sublimation. Then substituting for delta H equal to delta H sublimation by d delta V sublimation. So delta is nothing but delta H by t. Okay. Then the delta H sublimation divided by t by V bar gas. Okay. So the sublimation change in volume is same as the volume of gas. Okay, sublimation is nothing but the solid to gas. Okay, so the change in volume is nothing but the same as the molar volume of gas, because the solid molar volume is very very less, so change is same as the molar volume of gas. Okay, so you can substitute the change of molar volume of sublimation with the molar volume of gas, assuming ideal gas. Okay, so if you assume the ideal gas behavior, the molar volume is RT by B. Okay, so then dp by dt equal to pressure into delta H sublimation divided by RT square. And so take the TP outside and nothing but d ln P equal to d ln P by dt equal to delta H sublimation divided by RT square. This is the Clausius Capron equation. Okay. For liquid gas, replace delta H sublimation with delta H vaporization. Okay. For liquid to gas, the delta H is nothing but delta H vaporization. Okay. So this is the Clausius Clapeyron equation. So just changing the variables. Okay, so these are important when the relates the temperature difference of the vapor phase of liquid or solid to the delta H evaporation. Okay, this is the temperature dependence of pressure with the vapor delta H evaporation. Okay, so these are these are problems come. Okay, so you should know this. We can make another approximation assuming delta H sublimation independent of temperature. So if you differentiate with respect to integrating P1 to P2, you can take the delta H outside, you get the relation T1 to T2 minus T1 by T1 T2. Okay. This is integrated Clausius Capron equation. So this is also very much important. So if you integrate these two, you get ln P. Okay, so ln P ln P into pressure P1 and P2. Okay, so if you substitute ln P2 minus ln P1 equal to ln P2 by P1, like that you all know the simple mathematics. Okay, for liquid gas, replace delta K sublimation with delta K vaporization. Okay, okay. In practice, this is how you determine vapor pressure over a liquid or a solid as a function of temperature. Okay, how the vapor pressure change over a function. Problems have the two following forms. Okay, normally you know the temperature pressure for a solid gas or liquid coefficient and want to know the delta gas sublimation and delta gas vaporization. You know the temperature pressure one and delta gas sublimation and evaporation for solid gas coefficient, then you should know the temperature and pressure at coefficient lines. Okay, these are like problems. Okay, how they, if you give these two, you could you should calculate this. If you they give these two, you can calculate these two. Okay, simply using the formula. Okay, this allows you example, for example, to calculate the boiling point in Denver is 97 degrees Celsius. Okay, effect of internal inert gas pressure on vapor pressure over a liquid or solid. Okay, effect of inert gas pressure on vapor pressure over a solid or gas. Okay, total pressure is P equal to Pa plus P inert. Okay, if you take a pure air gas, this is vapor and this is liquid. Okay, when you when you add a inert gas at pressure, okay, P inert, and if you add a inert gas, what is the change? Okay, the effect of inert gas inert gas pressure on vapor pressure over a liquid or solid. Okay, P0 is equilibrium vapor pressure of pure air at a temperature T. Okay, and Pa is equilibrium partial pressure of A in the pressure of inert gas, in the presence of inert gas. At equilibrium, chemical potential of gas and liquid is same. Okay, then take the formula fundamental equation and differentiate with respect to pressure at constant temperature. You got the molar volume. If you differentiate with respect to pressure at with the constant temperature equal to d mu a divided by dpa divided by dp at constant t. Okay, so these integrals are same. Okay, so if you cancel these two, you get the same. Okay, okay, so differentiating with respect to the pressure at constant temperature and differentiating partial pressure with respect to pressure at constant temperature. Okay, then this is nothing but delta mu a at constant pressure. Okay, this is nothing but same. Okay, and this is the delta pa divided by delta p at constant temperature. V bar delta pa divided by b equal to molar volume divided by volume of liquid of gas. Okay, so it is greater than zero because liquid volume is small, gas or molar volume is higher. Okay, so presence of inert gas increases the gas, okay, away from critical point, so that effect is small. Okay, the same formula. So differentiating with respect to pressure at constant temperature, you got V bar you can write these two different differentiation. Okay, first differentiating chemical potential with respect to partial pressure Pa and differentiating partial pressure with respect to pressure, get the same relation. Okay, so this is, so the chemical potential of gas and liquids are same. Okay, that is at equilibrium these two are same. Okay, so this is nothing but the V bar. Okay, so V bar gas and dou Pa divided by dou P at constant temperature equal to volume of liquid. Okay, this is nothing but equal to volume of liquid. Okay, so these two are same. Okay, so then the relation ratio between volume of liquid divided by gas is greater than zero because both are positive value, so dividing to positive value will always give you the positive value, okay. But if you know the gas volume is greater than the liquid volume, okay, so then we get a small number, because below uh, greater value means you get a 0 point like that, so small value, so you get a very small effect, okay. So presence of inner gas increasing the pressure, okay. PA. Okay, so like if you get a positive value means increasing the pressure increases the pressure. Okay, it is a positive slope. Okay, positive value means positive slope. Okay, so that you can increasing the pressure. This is pressure. This is partial pressure PA. So increasing the pressure, it is a positive slope. Okay, so increasing the pressure increases the PA. Okay, like if an ideal gas, if A an ideal gas mean you can use the ideal gas law. Okay, then differentiating, see integrating with respect to Pa to P, P0 to P, you get the relation. Okay, so like for example, for mercury partial pressure is 0.27 tar at 100 degrees Celsius. Okay, pure mercury, 0.27 tar at 1 bar and total pressure, 0.28 tar at 100 bar total pressure. Okay, meaning that when increasing the pressure, the partial pressure increases but does not very much. Okay, 0.272, 0.2701 to 0.2830. So how much? 100 bar increases, but the pressure changes, partial pressure changes very much slow. Okay, so already told the using these relation you can say that. Okay, so it is very small. Okay, so the does not the it is very small. Okay, so increasing the pressure does not increase the pressure very much. Okay, okay, simple mathematics. If you know the mathematics, otherwise these concepts become very tough for you. Okay, simple differentiation, integration, graph when the slope is steep or like that, so you should know. Like simple problem, yeah, drug molecule has been synthesized and its phase diagram need to be exploring. Near its triple point, it is found that vapor pressure over the liquid PL and over solid is, so here near the triple point they give the vapor pressure of liquid and solid. Okay, so then calculate the triple point temperature and pressure, triple point pressure. Okay, set pressure of solid equal to pressure. Calculate triple point temperature and triple point pressure. Okay, set ln ps equal to ln p liquid. Okay, from this relation you can derive for solve, if you solve for temperature you get triple point temperature and triple point pressure. Okay, is renal a solid, a gas or liquid at 1 bar and 291 Kelvin. Okay, phase diagram, so it's a gas. Okay, so if you take triple point pressure is 11.1 bar and temperature is 279 Kelvin. Okay, at 1 bar and 298 Kelvin you should be in the gas phase. Okay, so the at a normal temperature and it is 1 bar and it is the normal temperature and pressure. Okay, so it is in a gas phase. Okay, phase diagram suits must be seen slope of coexistent curves are always positive. Okay, what is delta H for sublimation? Okay, use the Clausius Clapeyron equation, d ln ps divided by dt equal to this is, so just differentiating with respect to temperature means the first term only. So they give the relations. Okay, they give the relation, so just differentiating with respect to temperature you got d square. Okay, minus 1 by d square, so the minus will cancel out and this is nothing but the Clausius Clapeyron says the um, d ln p divided by dt is the delta h divided by rt square. Okay, so then the t square cancel out, delta h is equal to r into um, 3820 Kelvin. Okay, you get 31.80 kilojoules. Okay, using Clausius Clapeyron equation. So if you know the relation between the pressure and temperature, then you know the delta H like that, and the phase diagram, all that you can all calculate using the these thermodynamic relation. Nothing but these are nothing but the mathematics. Okay. Okay. So another example RDX. Okay, if you take RDX, so it is a explosive. You know that it's a explosive. So if you want a detector, if you detect the RDS, having accurate knowledge of its vapor pressure as a function of temperature. Okay, so actually the detector how it work is it detect the vapor pressure. Okay, it detect the vapor pressure at room temperature. Okay, so if you the vapor pressure of data for RDX are shown in the diagram. Okay, if you take this is the vapor pressure diagram. Okay, so RDX. Okay, RDX data points in dots and Clausius Clapeyron fit and 98% confidence limit and 98% prediction limit. Okay, so this is at 300 Kelvin. Okay, so normal room temperature. So if you plot the graph and you get pressure. Okay, and pressure so 10 power minus 10 or minus 11 bar approximately. Okay, 10 parts per trillion. So the instrument should be so accurate that it determines the vapor pressure. Okay, so 10 power minus 10 bar means very accurate. Okay, so bar approximately 10 power 11 bar. Um, it is used to detect the bomb detector. Okay, so in bomb detector, the RDX compound vapor pressure is determined at room temperature. Okay, that is how they determine the bombs in the. Okay, so in the vapor pressure, the compound sublimate. Some compounds are sublimate. Okay, rather than evaporation from the liquid phase. Okay, sublimation. Okay, we detect that we detect the vapor pressure and as a function of temperature. So these compound has a unique vapor pressure. Okay, so you can determine differentiate from other compounds. Okay, this is how they work. Okay, the two component phase equilibrium, understand and predict effects of mixing of substance on vapor pressure and boiling point. Effect of mixing of substance on vapor pressure and boiling point and freezing point. Okay, so if you mix the some substance. Okay, like binary liquid gas mixture. Okay, if you take a liquid, the mole fraction of a is xa and the mole fraction of b is xb is nothing but 1 minus xa. Okay, so total number of variable is 4: t, temperature, pressure, and xa and ya. A is the gas, b is solvent. Okay, so liquid gas mixture. So here total number of variables 4. Constraint due to coexistence. So at equilibrium, the chemical potential of liquid and gas are equal, and B chemical potential of B also same. Gas and liquid are same. So two constraint. Okay, so number of independent variable is, so the total variable 5 the minus constraint 2, 4 minus 2 equal to 2. Okay, so only 2. So example, if you know the temperature and pressure uniquely, then you can determine the composition in the liquid and gas phase. Okay, you can determine ya, yb and xa and xb. Okay, because there are two constraints. Okay, so then derive the equations. Generalize gives phase rule, gives the number of independent variable needed to describe a multi-component system where different phases. For a multi-component system, if you take, this is the formula how to we can derive this. Okay, f is the degrees of freedom, independent variables, and C is the components, number of components, P is the number of phases. Okay, how do we get this? Suppose a system has C components and P phases. What are all variables? First the temperature and pressure. Okay, then in each phase alpha, so take each phase alpha, and each case each component it is specified by its mole fraction xa. Okay, for ith component mole fraction is xi, and if you summate all the mole fraction you get 1. Okay, so the composition of each phase is specified by c minus 1 variables. Okay, so with the phase p, we have p into c minus 1 variables including temperature and pressure. Total number of variables is So the composition of each phase is specified by C minus O. So if you add all mole fraction, you get 1. Okay. So the composition of each phase is specified by C minus 1 variables. Okay. So total number of components is C minus 1 variables. Okay. With the P phases, we have to multiply P into C minus 1 variables. Okay. So including temperature and pressure, you should add 2 variables. This is P into C minus 1 plus 2 variables. That is nothing but temperature and pressure. Now add constraint 2 to phase equilibrium. Okay. Chemical potential of each component is the same in all the phases. So chemical potential of each component same in all phases at equilibrium. Okay. So for component I, it is same for all phases. Okay. Chemical potential of it all 1, 2, 3 number of phases, maybe 1, 2, 3. In water, number of phases is liquid, uh, gas, and solid, like that. Okay. So if you take number of phases equal to P equal to, then the number of constraint equal to P minus 1. Okay. Okay, for C components, then multiply C into P minus 1 constraint together. So adding constraint and minus this is the total variables, and minus the constraint, you get the total degrees of freedom. Okay. So just a mathematics. If you slowly try to understand this. Okay. Like if you take a one component system like in water, the number of phase equal to 1 means the degrees of freedom is equal to 2. Okay. So if you put a number of P equal to 1, then you get 3 minus P. Okay. So F equal to 2. Okay. So then you can vary temperature and pressure in a plane. Okay. If you take like water phase diagram, you get in one phase means you can vary temperature and pressure. Okay. If you phase equal to 2 means F is equal to 1, you can along the coexistent curve. Okay. If you have P equal to 3 means F is equal to 0. If you put P is equal to 3 means component equal to 1. Okay. So 1 plus 2 equal to 3. So we reduce the formula to 3 minus P. No free variables. That is, at a triple point, you cannot vary the temperature and pressure to maintain the triple point. Okay. So only 1 point. So phase equal to 4 is impossible for one component system. Okay. 4 phases cannot equilibrium. Okay. So the problem may ask from these formulas. Okay. We should understand what is phase and what is component. Phase is like a liquid phase, water phase. Okay. Component is water. H2 is a component. Okay. If you mix the H2 with glucose, then H2 is one component and glucose is another component. Okay. The phase is liquid, solid, and these are phases P. Okay. The component is H2O, like that. Okay. Those are components. You should don't confuse with these. Okay. So Rowlett's law and ideal solution. A is a volatile solvent and B is a non-volatile solute. Okay, like water and antifreeze. Okay. So if you take A is a volatile solvent and B is a non-volatile solute, so then the number of A is XA and B is XB. Okay, 1 minus XA, and the only gas phase is A because B is non-volatile. So the gas phase only A is present. Okay. Then the Rowletts assume linear behavior. Okay, the partial pressure of A is nothing but it linearly depends on the xb. Okay, so when xb equal to 0, xb is nothing but the moles of A. 0 means the partial pressure of A is pure. Okay, so vapor pressure of A is pure. When the xb is tends to 1, 1 means the xb is fully xb. Okay, so then the vapor pressure is x is the mole fraction of B. So okay, if you take small amounts of impurity or non-volatile solute, like that, if you increase the into high value means the partial pressure decreases. Okay, that is the Rowlett law. So a linear dependence of solvent and solid do not interact. Okay, so like in a mixture of ideal gas, there is also there is no dependence. Okay, so in ideal gas, the partial pressure of Pa is nothing but Xa into P. Okay, so Xa into P. Okay, like that. Here, Pa is the partial pressure of A, and the Xa is the mole fraction of A. The Pa is the pressure at this is like the total pressure. Okay, so when the Xp is 0, okay, Xp, that is when Xp added, the pressure decreases. Okay, then the Pa is Pa star. Okay, so Xa is nothing but 1 minus Xb. Okay, Then application of vapor pressure lowering, our first qualitative properties. Okay, when the difference PA star divided by PA. Okay, so PA is at when XA is XP added, PA star is when there is no XP. Okay, pure XA. Okay, difference in PA star equal to PA. PA is nothing but XA into PA star. XA is nothing but 1 minus XP. Then you get 1 minus XA. You take the PA star outside, 1 minus XA. 1 minus XA is nothing but XP. So XP BA star. This is greater than 0. Okay, because both are positive value. So greater than 0. Then what it means this is greater than 0 means the PA star is greater than. Okay, this is greater. Okay, then only you get a positive value. If PA is greater than, greater means you get a negative value. Okay, so here we get a positive value means here the PA star is greater. Okay, this is pure. Okay, this is when impurity order, that is vapor pressure lowered in a mixture. When impurity ordered, the vapor pressure are lowering. That is the colligative property. Impurity order, the vapor pressure lowering. Now consider let both A and B are volatile. If you take both A and B are volatile means when xp equal to 0, mole fraction 0 means there is no xb. Okay, so pa equal to b is 0. When xb is increases, the partial pressure of ba decreases, but the partial pressure of bb is increases. Okay, bb is, that is the pressure due to the b. Okay, because now b also volatile. Okay, so then b's concentration also increases in the gas phase. Okay, so you should know the difference between in the liquid phase, the concentration of A is XA and the concentration of B is XB. In the gas phase, it is YA and YB. Okay. So PA is nothing but XA PA star, PB is nothing but XB BB star. Okay. So P is total pressure is PA plus PB. Okay. So then add to XA and XB, adding mole fraction, you get 1. Okay. So ideal solution, both components obey Rowler's law. The diagram above shows the composition of the liquid phase. It does not provide information about the gas phase composition. It only it diagram shows the composition of the liquid phase, does not show the composition of the gas phase. Okay, so here this is the partial pressure of A and the pure partial pressure of B. This is the total pressure PA plus PB. Okay, coexistent curve. The gas phase is described by YA and YB. If temperature and XA are given, then YA and YB are fixed by Gibbs phase rule. That is, if temperature and composition of the liquid phases are known, then the composition and gas phase is determined. Okay, we can determine if you temperature and the composition and the liquid phase known, you can determine the gas phase. Okay, how to get YA? So PA equal to YA into P. Okay, Dalton's law. PA equal to XA into PA star. YA is the mole fraction at gas phase into total pressure P. Okay, PA at mole fraction. PA is the mole partial pressure of A. Okay, so another formula is this is from Rowler's law. This is from Rowler's law. This is from Dalton's law. Dalton's law is for gas, ideal gas. Dalton's law only for ideal gas. Okay, so in the gas phase you can make the ideal gas. Okay, so there is no much difference from ideal behavior. Okay, so you can use the Dalton's law. Pa equal to Ya into P. So that is nothing but Ya is what is Dalton's law? Pa equal to Xa into P. Means Xa is the mole fraction of A. Okay, don't confuse with the terms here. Xa, here Ya, here Xa. Don't confuse with the term. What is Xa? Xa is the mole fraction of A. Okay, it is the partial pressure. Pa means partial pressure of P. P is the total pressure. Okay, in the gas phase. Okay, so in the gas phase, partial pressure. Here in the liquid phase, mole fraction of A in the liquid phase, and this is the partial pressure of pure A. Okay, so what is partial pressure of PB equal to XB into BB star? Okay, so XB is nothing but 1 minus XA. So you should know what is mole fraction. If you have only XA and XB means adding these two you get to the 1. Okay, so then XB equal to 1 minus XA. Okay, so these are again and come and again you should understand. So then ya equal to pa by p. Okay, so here from take this pa equal to pa. So p is the total pressure, pa plus pb. Okay, so pa is nothing but xa into pa star. Here xa into pa star divided by pa equal to xa into pa star and pb equal to 1 minus xa into pb star. Okay, this is for ya. Ya is the mole fraction at gas phase. Inverting this expression just to modify simple mathematics. If you modify it, you get the mole fraction at solution. Okay, combining these two results. Okay, p is nothing but pa divided by ya. Okay, so then you get this relation. So all are mathematics. If you do the mathematics, you get the relations. Okay, this is summarized in the following diagram. Okay, so this is for gas phase, coexistent curve or dual line. Okay, combining both diagram into this is the for. Okay, this is for coexistent. This is the bubble line, the below is the dual line. Okay, so this is for liquid phase, this is for gas phase. So this line is used to determine the mole fraction of the liquid. The below bottom line is used to determine the mole fraction at the gas phase. Okay, so using the lever rule, you can determine the gas from the liquid phase to mole fraction to gas phase mole fraction. Okay, we can see the examples. Okay, two component phase equilibria, ideal and non-ideal solution. How do we use liquid phase binary mixture phase diagrams? Okay, we use them to find the composition of the gas and the liquid phases at coexistence. Consider again our typical diagram. A is more volatile than B. Okay, if you take A liquid and B liquid, and A is more volatile than B. Okay, so then the partial pressure of A is greater. Okay, because A is more volatile. Then more gases, more amount of A is there than the B. Okay, suppose start at 1 in the pure liquid phase. Okay, here if you take this, so as we decrease the pressure we eventually reach the temperature. Okay, so here if you take here, this is the pure A. Okay, so then decreasing the pressure, go to here. Okay, decreasing the pressure you get the liquid phase here. Okay, that is mole fraction xb. Then you take the at constant pressure, you take the straight line, you get the yb. Okay, this is the gas phase mole fraction. Okay, so just to take at a constant pressure. Okay, taking the pressure constant mean you take the straight line from this is the liquid phase curve, below is the gas phase curve. Okay, if you take the straight line you get the gas phase mole fraction. Okay, okay, so simple. So then decreasing the pressure further. Okay, so this is the pressure at pure, so then this is the pressure at 2, then decreasing the pressure further to 3, then you take the straight line you get the mole fraction at here. Now the mole fraction is higher than the 2, so this is the yb at 2, this is yb at 3. The mole fraction now increased. Okay, at the higher when the pressure decreases. Okay, so these are simple, so don't don't think these are hard. Okay, if you think these are easy means you can understand better. Okay, okay. Now how can you determine the quantities in each phase? Okay, what is the number of moles solution? Okay, if you take Na and Nb, number of moles of A and B, N gas and N liquid, the total number of moles of gas and liquid at 1. Okay, if you take this, that this is at 1. Okay, at 1 pure gas. Okay, so already told you below curve is the gas phase and the above curve is for liquid phase. Okay, at Na equal to Ya into Ng. Okay, Ng is the N total. Okay, so N total gas, pure gas only. So the total number of moles are only gas, no um no liquids. Okay, so one the nothing but Na is equal to nothing but Ya into N. Okay, So nothing but mole fraction Na equal to Ya into N total mole. Okay. So the and at two here at two the gas liquid mixture. Okay. So now the Na is nothing but YaNg gas plus XaN liquid gas. Now the gas and liquids are both exist. Okay. So then you so this take these two are equal. Okay. So this is equal to this is total because both are Na. Here also Na. Here also Na. So we can equate this N total equal to Ya to Ng plus Xa. Okay. You can equate these two and slightly rearrange these. You get these relations. This is the rubber rule. Number of moles of gas divided by number of liquid is Xa at 2 minus Ya at 1 divided by Ya1 minus Ya at 2. Okay. This is the ratio of lever arms. Okay. So if Xa at 4 equal to Ya at 1, then Ng4 equal to 0. No more gas. Okay. Like that, if you go in the diagram, how when the if you go in like that here, if you go this position, then both are equal. Okay, so the gas phase and liquid phase become equal because two curves are meeting each other. Okay, so then the gas phase equal to 0. No more gas. Okay, here only liquid are present, only here PBR, no gas are present, only liquid phase are present. Okay, these are simple mathematics. You should try to understand. Okay, instead of temperature being constant in the diagram above, we can fix the pressure also fixed. Okay, so when the pressure fixed means then we can plot a temperature versus mole fraction. Okay, then this is for gas phase and this is for liquid phase. This is bubble line. This two line. Okay, this is if you this is just the opposite for the pressure. Okay, so if you plot again pressure, then the above is liquid phase, the below is gas phase. When the plotting temperature versus mole fraction, you get this. So if you keep A is more volatile than B means the temperature is low. Okay, because more volatile means less temperature is needed to volatile the substance. Okay, so Ta star is less than the Tb. Okay, Tb star is more than the Ta star. Okay, okay, and the arguments for the pressure composition diagram now apply to the temperature. Same argument apply to temperature composition diagram also. Pressure composition diagram same apply to. Okay, so temperature composition diagram explains the distillation. Okay, in the distillation you using temperature you distillate the composition. Okay, distillate gas phase to liquid phase. Okay, because you increase the temperature the gas composition vary, and if you cool suddenly cool, you can separate the single liquid from another liquid. Okay, from mixture to you can like in the organic you can separate the solvents. Okay, separating the solvent using the rotor evaporator. Okay, okay, in ideal solution that obey Rowler's are called ideal solution. Obey Rowler's law. Okay, ideal solution obey the Rowler's law. Okay, what does that imply about the chemical potential at coexistence at equilibrium? The liquid and gas are same. Okay, liquid chemical potential, gas chemical potential are same. Assuming ideal gas, then the mu a gas equal to mu a at a standard chemical potential plus RT ln PA. Okay, so then substitute these for these, then you get this relation. If the system were pure A, okay, pure A, then PA equal to PA star. Okay, for a mixture PA is nothing but PA by PA star. Okay, so by Rowler's law says that BA equal to XA into PA star. Finally, then for an ideal solution, this is the equation. Okay, chemical potential A in a mixture, chemical potential pure A plus mole fraction, this is plus RT ln XA. XA is mole fraction of A in the mixture. Okay, looks just like a mixture of ideal gas. Okay, like this is mole fraction of ideal gas. Okay, so except that the gases are replaced by liquid. So they expect the gas are replaced by liquid. Ideal solutions are same, but don't forget for ideal mixture for liquid solutions also the chemical potential are less than for pure. Okay, mixture for mixtures chemical potential of liquid mixture is less than chemical potential of pure liquid. Okay, always less than. Okay, don't forget, because here it is a negative value because xa is positive, say 0 point like that, and so ln is a negative value, so you get a negative, means this is always greater than the this value. Okay, okay, two component phase equilibria, ideal and non-ideal solution. If you take a liquid and b liquid and take the partition and delta H mixing. Okay, this is gives free energy before mixing, and this gives free energy after mixing. Okay, Na mu a plus x xp. Okay, so delta is mixing in nothing but G2 minus G1. So you get the relation nRT divided purely entropic as in a gas phase. G is nothing but VdP minus STT. Okay, so delta S mixing is nothing but dou delta G divided by dou T at a constant pressure. Okay, differentiating. So take the temperature and put the negative sign. Okay, delta H mixing in nothing but delta G mixing plus T delta S equal to 0. Okay, so no enthalpy change. All is due to entropy of mixing, because there is no interaction. There is no interaction mean there is no enthalpy change. Okay, but the gives free energy is negative due to only the entropy of mixing. Okay, the gives free energy change is only due to the entropy of mixing. The no, and change in volume, there is no change in the volume also. Okay, just like no change volume, just like ideal gas. Okay, okay, non-ideal solution. Take non-ideal solution in reality molecule interact. Okay, so take A and B. So for pure the chemical potential less than 0. For mixing, this is for AB and AB, mu AB mixed state. The delta U change in chemical potential is product minus reactant. Okay, the different determines how the solution depart from ideality. Okay, so positive deviation, when happen positive deviation, if you take example carbon acetone and carbon disulfide. Okay, so there is no interaction between these two. Okay, so the mixing is energetically not favorable in liquid phase. Okay, then delta G equal to nothing but delta U plus delta PV. So in the liquid phase this is nothing but this is 0. Okay, so there is no change in the volume. Okay, much difference in the volume, so you can declare. So delta H is approximately equal to delta U. Delta G mixing equal to nRT XA ln XA plus XB ln XB. Okay, so if you take this relation. Okay, delta G is nothing but delta U equal to uh, mu A plus 2, so n by 4 delta mu. Okay, okay, so simple mathematics. Okay, if you know, so here from this relation to this relation come. Okay, n is the total moles. Okay, okay, then if you now for it is greater than the ideal solution. Okay, so delta G mixing is greater than the ideal. Okay, so now see, so when there is no interaction, the pressure total pressure is also greater than the ideal. Okay, so the dotted lines are ideal, like from Rowler's law. The solid lines are for real gas. Okay, so the total pressure also same, greater than the partial pressure of PB, also greater than partial pressure of PA, also greater than the ideal behavior. Okay, partial pressure is greater than the ideal behavior. Okay, this is for ideal behavior. uh, so it is greater than the, so acetone is greater than the mole fraction of acetone into pure state. Okay, that is the total pressure also greater than the Rowland pressure. Vapor pressure is higher than the expected by Rowland's law. Okay, negative deviation when delta U is less than 0, when there is interaction between, like if you take acetone and chloroform, there is hydrogen bonding. Now the Mixing is favorable. Okay, now the mixing is energetically favorable because the hydrogen bonding are when there is interaction between the mixing is favorable. Then the deviation is negative. Okay, so now the total pressure and partial pressure are less than the ideal. Okay, less than the ideal. Okay, total pressure also less than the Rowland pressure. Okay, ideal dilute solution and Henry's law. Non-ideal solution are difficult to describe completely. Okay, so you can describe the limits at xp equal to 1. 1 means xp tends to 1 means only xp. Okay, tends to 0 means there is no xp. Okay, ideal dilute solution. Okay, okay, when the xp tends to 1 means mole fraction of cs2 equal to xp tends to 1. 1 means tends to 1 means more xp. Okay, mole fraction of xp tends to 1 means 0.9. Okay, tends to 1. If you take 0.9 means more xp. More xp means b is solvent. Okay, like only solvent. Okay, because it is tends to 1. Okay, at 1 there is only solvent, there is no solid. One only solvent, there is no solid at all. So it is obeys the pure Rowler's law. Okay, pb pcs2 is equal to xcs2 plus into p star cs2. Rowler's law, obey the Rowler's law. When xp tends to 0 means 0.1. Okay, like that is tends to 0, there is p is a solid tube, very small amount of solid. Okay, then the Henry's law applies. Now the partial pressure of cs2 is mole fraction of cs2 into Henry's law. So okay, so okay, Henry law constantly depends on the solvent and solid mixture and the temperature. It is different for different solvents. Okay, different solvent or solid system. So just like it is a kb, even though it depends on a also. Okay, just labeled kb, but it also depends on the a, the solvent. Okay, here b is solid, a is solvent. Okay, okay, positive deviation. So this is the example. So this is the solid curve is the real curve. What Rowland says at xp equal to 1. So this is, so take the here, if you take the line, this take the line. Okay, and extrapolate to the here. If you take here, if you take and here you see here. Okay, so this. Okay, and approaching the x equal to 1, xp equal to 1, you follow the Rowler's law, extrapolate. Here you extrapolate. Okay, dotted line extrapolate something here also. You can very much approximately same value. Okay, below that you can deviate very much from the ideal behavior. Okay, and Henry's law says that at 0 to 1. Okay, at 0 xp is equal to 1. So here the dotted line getting. Okay, so now also the real are approximately same in the region. So and approximately this region. So only you can determine approximately, and in the extreme end, one xb equal to 1 or xb equal to 0. Only in the extreme ends you can determine these variables. Okay, ideal dilute solution xa equal to 1, approximately equal to 1, Rowler's law. Approximately equal to 0, 0 you can use Henry law. In the Rowler's law, pa is the partial pressure of pure partial pressure. In the Henry's law, it is a constant. It remains for different solvent and temperature and different solute. It is a constant measured. Okay, and this is the partial pressure at kb. Okay, total phase diagram: ideal, gas phase, liquid phase, and gas phase. Totally, if you saw total, the liquid phase and solid phase go both are. If you take the dotted lines are real ideal behavior. The real behavior is slightly less than the both. Okay, the both in the liquid phase and gas phase, the partial pressure is less than the ideal gas. Okay, okay. So stronger non-ideality. Okay, so when the curve are meet each other. Okay, here if you take this temperature, the gas phase and liquid phase are above this temperature you cannot separate. Okay, so that is the azeotropic mixture. Okay, you cannot distillate fast azeotropy after azeotrope you cannot distill it out, okay, because if you after that if you decreasing the temperature also, you cannot separate the mixture, okay. Okay, so we can these are only overview, okay. So we can see these topics in detailed in subsequent classes, okay. So here you should know the so this is for a broad view, okay. So broad view of, so then you can specifically if you explain this topic very closely, you can understand better, okay. So now you should know the broad view, okay. Okay, qualitative properties. So these are properties of solution in the dilute limit where there is a solvent A and solvent B, okay. Solid B, okay. So dilute means the solvent is greater than the solid B, okay. So these properties are a direct result of mu A mixing also. We know the chemical potential mixer always less than the pure, okay. Okay, use the two measures of concentration. Mole fraction is xb is nothing but Na divided by nb divided by total mole Na, okay. Okay, molality mb equal to moles of solute divided by kg of solvent. Molality is nothing but moles per solvent, okay, kg of solvent, okay. So Na is the moles of A and Ma is the molar mass in kg of 1 mole of solvent, okay. Okay, so these are no nothing moles into molar mass equal to number of kg of solvent, okay. Okay, there are four qualitative process: vapor pressure lowering and boiling point elevation and freezing point depression, osmotic pressure, okay. Now let's go these one at a time. First, vapor pressure lowering, that is Rowlett's law. So where you know from Rowlett's law, Pa equal to Xa into Pa star, okay. Xa is nothing but 1 minus Xp. So change in pressure Pa minus Pa star equal to here, okay, minus Xp into Pa star, okay. So Pa is nothing but Pa star, okay. Pa is nothing but 1 minus Xp into Pa star. Pa star nothing but Pa, okay, Pa minus Pa star equal to minus Xp into Pa star, okay. So if you do the mathematics, you get the answer, okay. This is less than 0 because it is negative, okay. So less than 0 means the Pa star is low than the Pa, okay. This is the highest value. So that is the lower pressure of it. This is lowering, okay. So that is the vapor pressure lowering, okay. Boiling point elevation. So from this relation you can derive the boiling point elevation. Okay. Mm, so for liquid, pure liquid, this is formula mu a star divided by RT ln Xa. For gas, this is same. So take this gas in this side and you get the ln Xa, okay. For ln Xa, so this is nothing but the delta G, okay. Mu gas divided by mu liquid is delta G, difference in chemical potential. So chemical potential gives energy are same, okay. Okay, so divided by RT, okay. Just like that, if you do the mathematics, you know this, okay. Simple mathematics, okay. So then you got, if you do derive the all these, you get the relation, okay. Okay, simple mathematics. If you ln x is equal to ln 1 minus xb, okay. Xb is very small, okay. Then ln of xb is approximately equal to minus xb, okay, like that. So all are simple mathematics you should know. Then Na by xb is nothing but nb divided by Na plus nb. So now nb is very small, you can take outside, okay. So neglect the nb, okay. So nb by Na, so this is nothing but mna divided by nmb. So m is the total mass. So then uh, ln x is equal to mb into ma, okay. So if you take time and do the mathematics, you get the relation, okay. Okay, for this is for delta mb is the mole changing, okay. So at a pure state, this is 0, mb is very small, okay. Then delta T is the difference in temperature. Okay, kbmp. Okay, freezing point difference is just the same occurring above. Just replace delta G vaporization with delta H freezing, and delta H vaporization freezing, and TB with the TB, and KB with the KF. Okay, so what is osmotic pressure? So if you take some A plus B in a membrane and A pure A in liquid, okay. So in the B point here, if you in the B, the pressure is P external plus L rho G. So this is due to length into have density into gravity. Okay, so pressure due to. So in inside the membrane, the pressure is P plus osmotic pressure. Okay, so there the now the concept osmotic pressure comes. Okay, P plus pi is the osmotic pressure. Here equal to P external plus L rho G plus H rho G, because due to this is the H distance H. So rho G, rho is the density and G is the gravity. Okay, so at equilibrium, these two are same. Okay, so using the Rowler's law, and take this to this side, and this is nothing but the delta G. Okay, the same calculation at a constant temperature, delta G is equal to VTB, and delta mu A equal to, so just dividing both sides divided by n, you got delta mu A equal to VA dP. Okay, then integrating with respect to temperature, you got this pressure P to P pi. You got so p plus pi minus p equal to pi. Okay, so you got pi. Okay, this as is incompressible liquid where volume does not depends on pressure. Okay, you see the volume does not depend on the pressure p. Okay, only osmotic pressure pi. Okay, so then delta G, you can use the delta G equal to VAP equal to minus 0. Again using ln XA approximately equal to NB divided by NA. Then RT minus NB divided by NA plus VA by NA equal to 0. Okay, just divide all this by NA. Okay, here NA, just divide all this by NA, you get the relation. Okay, okay, these are simple mathematics. Volume equal to VA plus VB. Then finally this is important. Okay, so this is like PV equal to nRT, ideal gas law. Okay, so here like N equal to N of P RT, and P is nothing but the partial osmotic pressure pi. Okay, this is quantum coefficient look like ideal gas law. If you replace C bar equal to NB by NA. Okay, so this is molar concentration is moles per volume. Okay, so then you got the quantum of equation. Thank you. If you refer the book Atkins and this topic, you can understand better. So we can see this topic one by one later. Okay.